Okay, this video is about concavity. Concavity is tells us if a function is concave up or concave down. And so we use the derivative to determine the concavity of a function. So we just have the function and we can calculate whether it's facing up or down. So concave up is if the derivative is increasing. So if f prime is increasing, or that's also to say that the slope is increasing. That's not necessarily to say that the slope is positive. The slope can be positive or the slope can be negative, but is it increasing? So what we're really concerned here with is the second derivative. How is the first derivative changing? Is it increasing or is it decreasing? So the way we determine concavity is if f, in this case, we're talking about up. So say if f prime is increasing or if f double prime is greater than 0. That's saying the same thing, but what we're concerned with is the second derivative being greater than 0. And I'll show you what I mean by that. So this is concave up. This is what it means to be concave up. It's facing upward. We can see that the slope is negative here and positive here, right? But what's happening as you go down, it's getting less negative, so it's increasing. And here it's 0. Then it becomes positive, and then it gets more positive and more positive. So the derivative is increasing, or the slope is increasing, or f prime is increasing. So f double prime is greater than 0 means it's concave up. And the same, obviously the opposite is true. If it's concave down, then f prime is decreasing, or f double prime is less than 0. So I'm not going to write that out. You can write that in your notes if you want. But we need to talk about what happens if, so at some point you have something that's concave up, and then at some point it becomes concave down. So if we have a function that looks like this, there's this point at which it changes, and we call that an inflection point. So c, some number c, is an inflection point if f double prime of c is 0. So the second derivative is 0. That's called an inflection point. Or if f double prime of c is undefined or does not exist. So if the second derivative doesn't exist, or if it equals 0, and at the same time the graph changes from increasing, from concave up, we'll say from concave up to concave down. And that's called an inflection point. So what happens is, the slope is increasing, as I showed you in this picture here. As you move along, it's increasing and increasing and increasing. At some point, even though you still have a positive slope here, it's now decreasing. It becomes 0, and then it becomes negative. So it's getting less steep and less steep and less steep, and then it becomes negative. So there has to be a point at which you stopped increasing and you suddenly started decreasing, and that's called, it's a subtle point. It's not as obvious as a critical point. Critical points, if you remember, are where the derivative is 0. It's at the bottom of the hill or the top of the hill. But this point is more subtle. At some point you stop increasing, you start decreasing. So that's called an inflection point. So we're looking for the second derivative being equal to 0. So I'll do one example, which I think is enough. So I want to determine concavity for, let's say f of x equals x to the 4th minus 4x to the 3rd. So in order to do that, I have to figure out where does the second derivative equal 0, and then I'm going to use a test point before and after to see if the second derivative is greater than 0, then I know it's concave up, and if it's less than 0, I know it's concave down. So this is similar to what we did earlier, where we were finding if it was increasing or decreasing. We used the first derivative around the critical points. Here we're going to use the second derivative, and then we're going to test points before and after. So f prime of x That's easy enough. That's 4x to the third minus 12x squared. F double prime, second derivative, is 12x squared minus 24x. If I factor out what they have in common, which would be a 12x, I will get x minus 2, x minus 2 equals 0. And I can see that there's an inflection point at x equals 0, x equals 2. So that's where the second derivative equals 0. I'll test a point just before that, so I'll try f double prime of -1. I want to see what the derivative is. When I plug in -1 into the second derivative, if you calculate, you'll see that it's greater than 0 or it's positive, which means it's concave up. If I choose a number between 0 and 2, like f double prime of 1, I see that it's less than 0, so it's concave down. And then I choose a number after. You can plug these numbers into the second derivative and you'll see is greater than 0, so it's concave up. And I just want to sketch it for you so you can see what this graph is doing. It's going, so this is 0, this is 2 here. It's going like this. Sort of like that. Didn't draw that well, but that's what's happening there. And you can see here is concave upward. It doesn't continue to go upward, but it's still at this point concave upward, which means the slope is increasing until it gets to 0. Then it's concave down right here. So we have an inflection point here, an inflection point here, and then suddenly it's concave up again, and it continues that way. So from 0 to 2, it's concave down, just as we said here, up, down, up. And that's concavity. It's just using the second derivative, similar to what we did earlier, and we're looking for inflection points instead of critical points. And that's concavity.